live interaction session for 11th week of our course, Computational Fluid Dynamics, by Professor Srinivas Jayanti, Department of Chemical Engineering, IIT Madras. I am your TA, Manjunath, research scholar from the Department of Applied Mechanics and Biomedical Engineering, IIT Madras. So let's start our session. So we are currently looking at the course content for week 11, in which we have discussed about the course. In the course, professor is discussing about finite volume method and also basics of grid generation. And we know the importance of grid generation in CFD method. So the difference between different types of grids and how important is the grids for the accuracy and also successful simulation of CFD of any particular flow problem is understood by everyone. So these are the topics that we will be discussing in detail, or seeing different questions from these topics. The questions will be discussed in our session. So let's start our session for today's. So first question: for the solution of Navier-Stokes equation in irregular geometries, which of the following grids can be used? So it's a basic simple question. So uh, the question is asking for solving Navier-Stokes equation in irregular geometries, which of the following grids can be used? 1. Cartesian grids, 2. Structured grids, 3. Unstructured grids. Options are option A 1 and 2, that is Cartesian grids and structured grids. Option B is 2 and 3, that is both structured grids and unstructured grids. Option C, all of the above, Cartesian, structured and unstructured. Option D, only unstructured grids, only 3. So it's basically a simple question. Try to recollect what we have learned in the course and try to answer the question. Please inbox your answers. So our answer is option B, that is 2 and 3, that both Cartesian grids and both structured and unstructured grids. So Cartesian grid is a subset of structured grid. So basically for irregular geometries we can use either structured or unstructured grids. So that is our answer is option B. Selecting choices 2 and 3. That is structured as well as unstructured. Next question. Which of the following can be claimed as an advantage of unstructured grid method of solution over a structured grid solution? Options statements are: first one, ease of grid generation; second statement, ease of grid refinement; third one, ease of solution of discretized equations. The question is asking advantage of unstructured grid over structured grid. Options are option A 1 and 2, that is ease of grid generation and ease of grid refinement. Option B 2 and 3. Option C all of the above. Option D only third. So try to find out the which of the following among the statement which all are the advantages of unstructured grid method over a structured grid. You can inbox your answers. The answer is option A, that is ease of grid generation and refinement. So basically unstructured grids are mostly if you see it is a triangle in 2D, triangle in 2D, and tetrahedral tetrahedrons in 3D. So these two elements, triangulation and tetrahedron making, is comparatively comparatively less complicated and easier method for grid generation. Also, when we are doing the grid refinement studies, we will have to subdivide these existing elements. Also, that will also become easier for unstructured grids. Whereas in structured grid solution, uh, the use of grid generation and refinement will be more difficult compared to uh, unstructured grids. So our answer is option A, statements 1 and 2. Next question. Which of the following statement is not true about so my mouse is not so not true when we use a structured grid flow through a complex geometry. So the question is asking which of the following statement is false for when we use a structured grid for flow through a complex geometry. Statements are: first statement, body fitted grids can be used only on two-dimensional geometries. Second option, finite different techniques cannot be used. Third statement, the diagonal dominance condition of the coefficient matrix is preserved. So, which of the following statement is not true when we used a structured grid for flow through a complex geometry? Options are: option A, only third statement; option B, statements 1 and 2; option C, statements 2 and 3; option D, statements 1, 2, and 3. So, try to find out which of the statements are not true regarding using a structural grid for a flow through complex geometry. You can inbox your answers. Our answer is option D. That is, all the three statements are not true regarding when we use a structured grid for a flow through a complex geometry. Body fitted grids can be used in three-dimensional also, and we can also use finite difference techniques, but mostly we don't use, but cannot and don't is different thing. So second statement is also wrong. And uh, diagonal dominance condition matrix preservation, this statement is also not always correct. So all the three statements are wrong. So our answer is option D. That is all of them, all the three statements. Here also option D. Okay, moving to next question. Which of the following statement is not true about the transformation of Laplace equation into a non-orthogonal curvilinear coordinate system? So question is asking about the transformation of the Laplace equation into a non-orthogonal curvilinear coordinate system. Options are: first option, the elliptic equation remains elliptic. Option B, the elliptic equation becomes parabolic. Option C, the elliptic equation becomes hyperbolic. Option D, the parabolic equation remains parabolic. So, so, so the question is asking uh, when we are transforming uh, Laplace equation, uh, in a non-orthogonal. That is, the coordinate system is non perpendicular and it is converted to a curvilinear coordinate system. Then what will be the effect? Uh, what is the effect of the transformation in the equations? Options are: the elliptic equation remains elliptic, the elliptic equation becomes parabolic, the elliptic equation becomes hyperbolic, the elliptic equation remains parabolic. So which among the following is true about the transformation? You can try to answer the question. You can inbox your answers. Okay. Our answer is option A. That is, uh, elliptic equation remains elliptic. We know that Laplace equation is an elliptic equation, and the transformation of coordinate system won't affect the equation, basic equation type. So the elliptic equation will remain elliptic. So our right answer is option A. So when we transform a non-orthogonal from a structural grid to non-orthogonal curvilinear coordinate system, the fundamental nature of the equations won't change, whereas the coordinate transformation will only affect the form of the equation, that is the coefficients. We know that when we are changing partial differential equations into algebraic equations, it will have a set of coefficients. So these coefficients will be affected by the transformation, not the actual type of partial differential equation. Okay, so hope that's understood. Move to next question. The next question is on ADA scheme, that is alternating direction implicit scheme. So the question is asking which of the following statement is true about the alternating direction implicit scheme. Statements are: first statement, it is an iterative method. Second statement, it requires diagonal dominance for convergence. Third statement, it can be applied to three-dimensional problems. So you which have watched the videos, and the ADA scheme is discussed in detail there. So the question is asking which of the following statement is true about ADA schemes. Is it an iterative scheme? Second statement, it requires diagonal dominance for convergence. Third statement, it can be applied to three-dimensional problems. Options are: option A, first and second statements; option B, second and third statement; option C, first and third statement; option D, all the three statements. Try to answer the question. You can inbox your answers. Question is about ADI scheme, also known as short form for alternating direction implicit scheme. Our answer is option C, that is first and third statement. Uh, it can be considered as an iterative method, and also uh, it can be applied to three-dimensional problems. While the diagonal dominance is desirable, but it is not uh, absolute necessity for ADS scheme. So statements 1 and 3 is true. So option C is right. Next question. For the solution of Ax is equal to B, which of the following decomposition of matrix A is the most implicit? So we know that this is the uh, matrix formation of our system of linear equations, where A is the coefficient matrix, X is the unknowns, and B is the right side of the equation or the constants. So the question is asking which among the following is the most implicit decomposition of Ax is equal to B, or most implicit decomposition of coefficient matrix A. Options are option A, LU decomposition, option B, uh, incomplete LU decomposition, incomplete LU factorization, option C, LU plus N as in SIP, option D, Cholesky decomposition. So which among the following will be most implicit decomposition for matrix A? We have discussed LU and ILU in previous sessions also. From that, try to recollect and answer the question. You can inbox your answers. Our answer is option C, that is LU plus N as in SIP. That's SIP is the name itself. If you remember, SIP is the short for strongly implicit procedure. So LU plus N, where N is a perturbation matrix, uh, when this perturbation matrix is added to LU decomposition, the method becomes strongly implicit procedure. So among the options, option C, LU plus N as in SAP, that is strongly implicit procedure, is our answer. So this addition of this perturbation matrix n will improve the conditioning of the system, that is the system of equations, and it will help in the convergence of the uh, iteration process. Next question. The advanced iterative techniques are used primarily to enhance which of the following aspects of basic iterative methods? So we have discussed some of the advanced iterative methods in the previous sessions. So the question is asking what is the advantages of, or what is the uh, USP, or what is the need, or what is that the advanced iterative techniques are improving in the basic iterative methods. So the advanced iterative method will be some modifications of basic iterative methods. So what is that? What which among the following will be enhanced by using advanced iterative techniques? Option statements are convergence condition, second convergence rate, third ease of computation. Options are option A 1 and 2, that is convergence condition and convergence rate. Option B, that 2 and 3, that is convergence rate and ease of computation. Option C 1 and 3, that is convergence condition and ease of computation. Option D all the three. So try to answer the question. You can inbox your answers. The answer is option A, that is 1 and 2, convergence condition and convergence rate. These two will be enhanced by using iterative techniques. Mostly convergence rate is the primary target of advanced iterative methods, while advanced iterative techniques can sometimes broaden the range of problems for which convergence is achieved. The primary focus is not fundamentally altering the convergence conditions themselves, but to improve the convergence rate. The basic convergence conditions such as diagonal dominance, positive definiteness, all the things will be remain relevant, even though we will, if even after we have applied some advanced iterative techniques. So, uh, so uh, second one, that is convergence rate is the primary target. Doing so, some of the additional convergence conditions also may get altered. So, from among the statements, we can choose option A, that is statement 1 and 2. Moving on to next question. Which of the following statement is true about multi-grid method? So, this is asking which of the statement is true about multi-grid method for solving Ax is equal to B. Statements are: first statement, it uses multiple grids for the same domain. Second one, it uses multiple grids for the same equation. Third statement, it solves the same equation on all grids. The question is on multi-grid method, and you have to find which all the statements are true regarding multi-grid method. Options are option A, that is 1 and 2, statement 1 and 2. Option B, statement 2 and 3. Option C, statements 1 and 3. D, options 1, 2 and 3. So, which of the following statements are true about multi-grid method? Our answer is option D, that is all the three statement. That is multi-grid method uses multiple grids for the same domain, and yes, it do solves the same equation in all the multiple grids, and uh, it solves for all the grids. Moving on to next question. The Delaunay triangulation is a method for unstructured mesh generation that focuses on which of the following? Options are option A, creating elements with good aspect ratio. Option B, minimizing the total number of elements. Option C, maximizing the volume of each element. Option D, guaranteeing conformity with the computational domain boundary. So, which among the options below uh, best represents Delaunay triangulation method? So we have learned in the lectures that triangulation, Delaunay triangulation is a classic method for creating triangles or dividing our domain into triangles. So that's why it's called the triangulation method. So this is a classic method for creating unstructured mesh, uh, and it will create triangles in. Uh, uh, we have discussed earlier that it will create triangles in 2D and tetrahedrons in 3D. So the main method or main uh, objective of this triangulation method is to create elements with good aspect ratio. So our answer is option A. That is, the Delaunay triangulation methods ensures elements are well shaped. So this well shaped means with elements having good aspect ratio, which will help us in getting better numerical stability and accuracy. Next question. Next question is on advancing front method. The advancing front method for mesh generation is particularly useful for which of the following? Options are: option A, simple rectangular geometries; option B, complex geometry with intricate boundaries; option C, uniformly spaced grids throughout the domain; option D, refinement of existing structured meshes. So the question is asking the utility or usage of this advancing front method of mesh generation, where it is used. Options are: option A, for simple rectangular geometries; option B, complex geometry with intricate boundaries; option C, uniformly spaced grids throughout the domain; option D, refinement of existing structured meshes. You can answer the question. Try to answer the question. Inbox your answers. So the answer is option B, complex geometries with intricate boundaries. So this advancing friend method is another type of mesh generation method where the meshing will starting from one particular boundary and it will forward or it some boundaries and it will advance, keep on refining to the other sides. Whereas in Delaunay methods and all, the boundary should be uh, all the boundaries should be uh, accorded first. So our answer is option B: boundaries with complex geometries with intricate boundaries. Because when boundaries are intricate or very irregular, then this type of method can effectively handle the variations of shape in the boundary and can conform to uh, conform meaning it can um, create elements that is well suited to that particular boundary. Our answer is option B. Moving to next question. Next question is octree-based methods or mesh generation are well suited for which among the following? Options are option A, generating highly anisotropic meshes. Option B, adapting the mesh based on solution gradients. Option C, creating very fine meshes around small features. Option D, all of the above. So next other question is on another mesh generation method, that is octree based methods. So which among the following statement or which among the following statement is true for octree based methods? The answer is option D, all of the above. That is, octree based methods for mesh generation can generate highly anisotropic meshes. It can adapt the mesh based on solution gradients and it can also create very fine meshes around small features. And this octree based method, if you see, it's a kind of mesh generation where every single cell is subdivided into 8 subdivisions as if in 8 octants. If you see, if you know what is an octant, like then octet. Okay, sorry. It's like if you can think of a cube. So if we are cutting it into cutting in this way, uh, and also this way, so that is it is cut at the middle, horizontally and vertically, then this will create 8 uh, small cells, that is octants. So such kind of method is called octary based method. So all the above statement is true for octary based method, that it can subdivide the domains based into anisotropic meshes using any user defined criteria, and it can create refinement near small features, and also it offers an overall flexibility. So our answer is option D, all of the above. Next question. A key advantage of unstructured meshes compared to that of structured meshes in CFD is. So again, the question is on advantage of uh, unstructured meshes over structured meshes. So we have already seen similar questions, but every time the catch is in the options. So try to understand the options very well and then try to answer the question. Options are: option A, they are always computationally more efficient. Option B, they can accurately represent complex geometries. Option C, they require less user input for mesh generation. Option D, they are inherently more accurate for all CFD problems. So the question is asking a key advantage of unstructured meshes compared to structured meshes in CFD. Try to answer the question. You can inbox your answers. Okay. Uh, Our answer is they can accurately represent complex geometries. So the question is asking a key advantage. So the key over The foremost and important factor that we always go for unstructured meshes is that it can accurately represent the complex geometries. So if we are to use structured meshes for complex geometries with irregular boundaries, then it will be much computationally difficult to create such geometries. So at uh, at that conditions, the best method is to go for unstructured meshes. So our answer is option B, that unstructured meshes can accurately represent complex geometries, because these unstructured meshes can conform into intricate shapes, uh, while structured meshes will struggle to conform to complex boundaries. You will have to give prism layers or all other uh, growth factor or uh, cell growth factor and all similar things to capture complex boundaries for structured meshes. Moving on to next question. When choosing an unstructured mesh generation method for CFD simulation, a crucial factor is to consider is which among the following. Options are the total number of elements in the mesh. Option B, the compatibility with the chosen turbulence model. Option C, the level of automation offered by the meshing software. Option D, the ability to capture the expected flow features. So, while choosing unstructured mesh for CFD over a structured mesh, which among the following is a crucial factor to consider? Options are option A, total number of the mesh. Option B, compatibility with the chosen models. Option C, the level of automation offered. Option D, the ability to capture the expected flow feature. Try to answer the question. You can inbox your answers. The answer is option D, that is the ability to capture the expected flow features. So, first we have we have discussed that why we are choosing unstructured mesh over structured mesh, because it is able to capture complex geometries and ability to conform to complex boundaries. So, but if we are choosing unstructured mesh, then what is the crucial factor to consider? That was our question. So, the crucial factor to consider is its ability to capture the expected flow features, because the CFD mesh refinement and mesh sizing is very important to capture the expected flow features. So the ability to capture the expected flow features should be considered while uh, opting for unstructured meshes, because the unstructured meshes, the chosen unstructured meshes and mesh parameters should be able to resolve the important flow features like boundary layers, shocks, and all to give us a accurate result. Moving on to next question. Which of the following statement about mesh quality is generally true for unstructured meshes in CFD? So the question is about the mesh quality of unstructured meshes. Options are: option A, they always have better quality compared to structured meshes. Option B, they require more effort to ensure good element quality. Option C, they are inherently less accurate due to irregular element shapes. Option D, the special care is not needed for mesh quality with unstructured meshes. So the question is about broad question about mesh quality of unstructured grid uh, over structured grids, or general aspect of mesh quality of unstructured meshes. Our answer is option B, that is, they require more effort to ensure good element quality. So, regarding mesh quality of unstructured meshes, one key aspect is that it will require more effort to ensure good element quality, because unstructured meshes you can create poor create elements with poor aspect ratio, skewness, and skewness, etc. These are different parameters in mesh quality metrics, and creating poor quality meshes can impact the accuracy. So careful mesh generation and quality checks are necessary to uh, ensure that we have obtained a good quality mesh with unstructured mesh. Even though the unstructured meshing is easy, maintaining the quality uh, mesh quality is difficult with unstructured meshes. Moving on to next question. A common challenge associated with unstructured mesh adaptation in CFD is. So the question is asking about a limitation or challenge associated with unstructured mesh adaptation in CFD. Options are option A, maintaining good element quality after refinement. Option B, reducing the overall computational cost of the simulation. Option C, ensuring compatibility with the chosen flow solver. Option D, imposing complex boundary conditions on the adapted mesh. So, which among the following is a common challenge or common limitation associated with unstructured mesh in CFD? The answer is option A, that is maintaining good element quality after refinement. We have just discussed in the previous question that even though mesh generation will be easier when we opt for the unstructured mesh adaptation, but the maintaining of good quality elements or good element quality or mesh quality will be difficult. Uh, it will be become increasingly difficult when we are going for refinement, step by step refinement. We are continuously refining the mesh. The maintaining of good mesh quality or good element quality becomes a limitation or increasingly challenging process in unstructured meshes. Whereas in structured meshes, the structured meshes will initially itself the structured meshes will be structurally arranged. So then subdividing that for refinement, we can easily subdivide that particular mesh to get more refinement or increase the density. But whereas in unstructured meshes, again the splitting of the cells or splitting of the elements will be done in an unstructured way, which can uh, create poor element quality or poor quality elements. So our answer is option A. Maintaining good element quality after refinement is a challenge in unstructured meshes. Next question. Moving on to next question. In unstructured mesh generation, the process of assigning material properties to each element is referred to as. Options are option A, mesh refinement, option B, boundary condition assignment, option C, meshing convergence, option D, cell tagging. So in unstructured mesh generation, the process of assigning material properties to each element is defined as which of the following? Try to answer the question. You can inbox your answers. Our answer is option D, that is cell tag. So like putting tag to any of our merchandise or goods, um, but assigning metal properties to elements are defined or assigning metal properties to cells are called or referred as cell tagging. Option D is our answer. Moving on to next question. In the advancing front method for mesh generation, how does the front progresses through the geometry? So the question is on advancing front method of mesh generation. The question is asking how does the front progress through the geometry? Options are option A, randomly selecting points within the domain. Option B, iteratively adding points to the boundary and advancing inwards. Option C, dividing the subdomain, dividing the domain into predefined subregions. Option D, sweeping a structured mesh across the geometry. So the question is on advancing front method and how does the front in the advancing front progresses through the geometry. Try to answer the question, inbox your answers. answer is option B, that is iteratively adding points to the boundaries and advancing inwards. So the front meaning how the particular process is continued or progresses inside the geometry. So it will subdivide the points at the boundary, and with that it will advance inwards. It will start in the boundary and advance inwards into the inside of the geometry. So the advancing front method uh, first tries to subdivide the boundary into uh, uh, subdivide the boundary into smaller segments by adding points in the boundary, and then it will gradually fill the interior of the geometry. Next question, moving on to next question. The primary advantage of a body fitted grid in CFD compared to a Cartesian grid or complex geometries. The question is asking the primary advantage of body fitted grid compared to a Cartesian grid for complex geometries. So what is the advantage of using body fitted grid over a Cartesian grid for complex geometries? That is our question. Options are: option A, reduced computational cost; option B, improved accuracy near boundaries; option C, simpler implementation of boundary conditions; option D, easier mesh generation process. Try to answer the question. You can inbox the answers. The answer is option B, that is improved accuracy near boundaries. So uh, the name itself is intuitive. That's body fitted grid means the grids or meshes that will conform to the shape of the objects. So which will allow for smaller and more accurate cells near the boundaries where the flow gradients are high. So such body fitted grids will provide improved accuracy near boundaries. So our answer is option B. Next question. A well-designed body-fitted grid should have minimal skewness in its cells. What is the negative skewness of highly skewed cells? The question is a little confusing here. The question is first. The question is followed by a statement. Statement is a well-designed body-fitted grid should have minimal skewness in its cells. So the question is asking what is the negative consequence of highly skewed cells? Options are option A, increased computational efficiency, option B, improved flow visualization, option C, reduced accuracy of flow solutions, option D, easier post-processing of results. So which among the following is a negative consequence of highly skewed cells? So comparatively very, even though the question is confusing, the options are very easy. Try to answer the question. What is the negative consequence of highly skewed cells? So for the question, I mean options itself, it is indicative. So the question is asking for a negative consequence. So if you compare the options, all the three out of the four options are giving positive statements, that is increased efficiency, improved, and easier. So all these are positive terms. From that itself we can easily find out the answer. That is, our answer is option C, reduced accuracy of flow solutions. That is the negative consequence of highly skewed cells in a mesh, because these highly skewed cells can introduce numerical errors which can affect the convergence as well as the accuracy of the CFD solutions. Moving on to next question. Chimera grids are a type of body fitted grid used for which of the following? Options are simple geometries with smooth curves. Option B, overlapping or intersecting objects. Option C, highly viscous flows with large velocity gradients. Option D, turbulent flows with complex vortex structures. So the question is asking a possible application of chimera grids, which is a type of body fitted grid. So which among the following is an application area for chimera grid? Options are option A, simple geometries with smooth curves. Option B, overlapping or intersecting objects. Option C, highly viscous flows with large velocity gradients. Option D, turbulent flows with complex vortex structures. Excuse me. The answer is option B, that is overlapping or intersecting objects. So option B is our answer. And this chimera mesh is also called overset mesh. So this chimera is a type of body fitted grid used for overlapping or intersecting objects. This chimera meshes allows for patching together multiple body fitted grids for complex geometries with overlapping or intersecting components. Our answer is option B. Moving on to next question. When generating a body fitted grid, a clustering technique is often employed to which of the following? Options are option A, randomly distribute cells throughout the domain. Option B, increase the density of cells in region of high flow interest. Option C, reduce the overall number of cells in a mesh. Option D, simplify the grid generation process. So the question is asking clustering technique. What is the purpose of clustering technique used in body fitted grid? Options are randomly distribute cell throughout the domain. Option B, increase the density of cells in region of high flow interest. Option C, reduce the overall number of cells in a mesh. Option D, simplify the grid generation process. You can inbox your answers. Our answer is option B. So, by the word clustering itself, it's intuitive that we will be uh, what we will be adding, or we will be adding a lot of cells in a particular region. That is, clustering means addition or accumulation of something. So, uh, if you think in that basis, we can easily find out the answer from here. That is, increased density is something related to clustering or accumulation. So our answer is option B, increase the density of cells in regions of high flow interest. That is our answer, option B. Because this clustering of cells will allow uh, a refinement in particular area of our interest where we expect high gradients or complex flow phenomena. Com complex flow phenomena. So our answer is option B. Moving on to next question. Compared to body fitted grids, compared to structured body fitted grids, unstructured body fitted grids are generally. So here the question is asking a comparison between structured body fitted and unstructured body fitted. So we have previously answered similar question regarding only structured versus unstructured. So here the question is about structured body fitted and unstructured body fitted. Okay, our options are option A, more efficient for complex geometries. Option B, easier to generate automatically. Option C, more accurate for higher order numerical schemes. Option D, less prone to numerical errors. So try to answer in context of structured body fitted and unstructured body fitted measures. So the answer is option A, that is more efficient for complex geometries. Our answer is option A, more efficient for complex geometries. Structured body fitted measures will be more efficient for complex geometries rather than uh, structured grids will conform to intricate shapes more flexibly than the structured grids, which will make them best suited for complex geometries. Answer is option A. Moving on to next question. A major challenge associated with body fitted grid is. The question is asking a challenge or limitation of body fitted grids. Options are A. High computational cost due to complex grid generation. Option B. Difficulty in implementing turbulence model. Option C. Inability to handle moving boundaries. Option D. Limited applicability to inviscid flows. So, which among the following will create challenge for a body fitted grid? Try to answer the question. The answer is option A. High computational cost due to complex grid generation. So, high computational cost because in body fitted grid itself, uh, generating a body fitted grid itself is a difficult method. So it will uh, it will need a comparatively more computational resources compared to other methods of grid generation. So generating a high quality body fitted grid can be time consuming and computationally expensive process, especially for complex geometries. The answer is option A. Moving on to next question. Mesh adaptation, that is, refinement or coarsening of the mesh, is a technique used with both structured and unstructured grids. What is the main purpose of mesh adaptation? Adaptation, sorry, mesh adaptation. Options are option A, reduce the overall mesh size for faster simulations. Option B, improve the accuracy in areas with changing flow features. Option C, ensure all elements have the same aspect ratio. Option B, simplifying post processing of CFD results. So, the concept of mesh adaptation is refining or coarsening of mesh, refining or coarsening of mesh in different areas of the same mesh. This can be used with both structured and unstructured grids. So, the question is asking what is the main purpose of mesh adaptation? Options are reduce the overall mesh size for faster simulation. Option B, improve accuracy in areas with changing flow features. Option C, ensures all elements have the same aspect ratio. Option D, simplifying the post processing of CFD results. Try to answer the question. Answer is option B, that is improve accuracy in areas with changing flow features. So mesh adaptation allows for focusing computational resource on regions where solution is expected to change rapidly. So this called refining the adaptive mesh is like the mesh adaptation or adaptive mesh meshing technique is uh, a advanced meshing feature which will be a response to the flow physics, that is where the higher gradients exist or some uh, actual flow conditions are continuously varying or this complicated flow structures exist. Such areas will get refined, and other areas of lower importance will be coarsened. So such a method of adaptive meshing or mesh adaptation will help in increase the accuracy in areas of changing flow features while focusing to reduce the computational reduce to optimize the computational resources. Moving on to next question. A hybrid mesh combines elements of both structured and unstructured mesh. What is the potential benefit of using hybrid mesh or hybrid approach? We have seen that structured and unstructured grids. So, whereas hybrid mesh is something that will uh, combine elements of both structured and unstructured grids. So, what is the potential benefits of using hybrid method? Options are option A, improves accuracy everywhere in the domain. Option B, simplifies mesh generation for complex geometries. Option C, reduces computational cost significantly. Option D, eliminates the need for mesh refinement. Try to answer the question. The answer is option B, that is simplifies mesh generation for complex geometries. Because the hybrid mesh allows for structured elements around simple regions and unstructured elements around complex geometries, complex boundaries. Suppose it's like you have an irregular geometry or something. Suppose something like this. Then this near boundary or this particular region will be meshed using unstructured meshes to capture the uh, complex boundaries, whereas inside the simple regions will be meshed with uh, structured meshes. So this will help to reduce the simplify the mesh generation for complex geometries as well as it will optimize. It will help to optimize computational resources by improving the mesh quality. Moving on to next question. Is another question. Delaunay triangulation method. Delaunay triangulation is a popular method for unstructured grid generation. It ensures it's among the following. Options are: option A, all elements have the same aspect ratio. Option B, no interior angle of triangle exceeds a certain limit. Option C, the elements are distributed uniformly throughout the domain. Option D, the grid density is highest near boundaries. So, which among the following is a key objective of Delaunay triangulation? Options are: all elements have same aspect ratio. Option B, no interior angle exceeds no interior angle of the triangle exceeds a certain limit. Option C, the elements are distributed uniformly throughout the domain. Option D, the grid density is highest near boundaries. Our answer is option B, that is no interior angle of a triangle exceeds a certain limit. So, if you have used any uh, softwares or meshing softwares, then there will be for unstructured mesh settings there will be a option asking for interior angle or the maximum angle which we should set as some limit. So that is the main objective of Delaunay um, triangulation method. That Delaunay triangulation methods try to create well-shaped elements with no excessively acute or obtuse angle for better numerical stability. So the triangulation or the division of the domain or space is based on uh, limiting uh, limiting the range of angle or interior angle of triangles. Moving on to next question. The advancing front method for mesh generation involves which among the following? Options are: option A, dividing the domain into a set of octree cells. Option B, progressively adding elements from the defined boundary. Option C, constructing a grid based on a predefined set of points. Option D, defining an existing coarse mesh to achieve desired resolution. So the question is on advancing front method. So what is the purpose of, what is the process of advancing front method, or how advancing front method creates mesh? Options are: dividing domain into a set of octree cells. Option B, progressively adding elements from defined boundary. Option C, constructing a grid based on predefined set of points. Option D, defining an existing cosmos to achieve desired resolution. Try to answer the question. Our answer is option B, that we have already discussed in another question also. Progressively adding elements from a defined boundary. So in advancing run method, the it will try to divide the boundary by adding points to the boundary, and then it will iteratively add elements into the domain, and it will sweep from it will uh, uh, start from the boundary and uh, keep on generating cells inwards to the domain until the entire space is filled. So that is the method of uh, adaptive mesh refinement. Sorry, that is a method of advancing front meshing method. So that's all for today. Thank you everyone for joining.